Okay, well, maybe we'll get started. It looks like the people is slowing down. So our speaker today will tell us about the music of the spheres. Stephen Taylor is a professor of physics astronomy at Vanderbilt University in the country music capital of the world, Nashville, Tennessee. He was an undergrad at Oxford, graduated in 2010, then moved to Cambridge, where in 2014 he received his PhD on standard sirens and cosmology with gravitational waves and approaches to gravitational wave analysis with pulsar timing arrays. And his advisor, I know, was Jonathan Gayer, a former postdoc at Caltech in 2002 to 2004. Then after that became the JPL, was a postdoc at JPL with Joe Lazio, Michaela Vallisneri, and others, working on backgrounds and sources from pulsar timing arrays for gravitational waves. Then he moved down the hill to Caltech for 2 years, was a postdoc working on the NANOGrav project. In 2019, he moved to Vanderbilt, where he's been ever since, and also has continued working on NANOGrav, where he's currently the chair of the collaboration. For those of you not in the know, NANOGrav stands for the North American Nanohertz Observatory for Gravitational Waves. And all of that decades of work culminated last year with the release of the 15-year data set, which for the first time announced evidence of detection of a gravitational wave background from merging supermassive black holes. They're now looking for evidence of in-spiral wide separations driven by stellar and gas dynamics other than gravitational waves, and using galaxy catalogs to try to see if there's a particular source rather than many of them that are contributing significantly. Stephen received an NSF Career Award in this year's Cobley Lectureship at the American Astronomical Society, and he'll tell us about charting the gravitational wave universe at light-year wavelengths.
Thank you very much, Sterl. Thanks everyone for coming today. It's not lost on me that I'm the only thing that stands between you and the PMA holiday party, so I will do my best to amuse you to the extent that I can for the next hour. So I'm going to tell you a little bit about some things you might have heard already from the great NANOGrav and pulsar timing array people that are here, but also a little bit about new developments and where we might be going in the future. Before we get going properly, I want to set the stage for us understanding the spectrum of gravitational waves and what different detectors can probe those. So if you want to be sensitive to, say, compact objects, compact binary systems of different masses, then really you're looking at frequencies that scale inversely with the total mass of the system. So roughly speaking, you can think of the innermost stable circular orbit as the frequency at which things will merge quickly together. And so if you want to be sensitive to things that are more massive than what LIGO can see, you go lower in frequency. That means you start to enter into the millihertz band, where the laser interferometer space antenna will be sensitive in hopefully 2035. If you go even lower in frequencies, you get to the regime of nanohertz, where you're looking at making observations over years to decades. And the kinds of compact object binary systems that you're looking at there are the most massive systems in the universe. So these would be supermassive black hole binary systems of 10 to the 8 to 10 to the 10 solar masses. If you go lower than that, several more decades, you get to the regime of polarization probes with the CNB. So these are our frequencies, these are detectors, these are then our sources. As you go lower in frequency, you're going up the mass scale. And here might be a more familiar way of looking at this entire landscape. And it's the GW plotter, something that you probably used to make your own presentations in the past, but we've updated it with slightly more accurate sensitivity graphs for pulsar timing arrays. It's no longer a pizza red that is often put on these. It's something that actually shows the sensitivity at lower frequencies, reducing due to some fitting of pulsar characteristics, and then at higher frequencies, you've got limitations due to the measurement uncertainties or the radio pulses themselves. So this is the landscape of gravitational wave searches at the moment, with the promise of being filled in the middle with LISA in the middle to the end of next decade. Now, for pulsar timing arrays, the sources that we're using to perform gravitational wave searches are astronomical sources. So one end of our detector is on the Earth. Those are the radio telescopes that look at the sources. but pulsars themselves are a key component of our detector. I'm sure everyone in the audience knows what a pulsar is and its characteristics, but they were discovered in 1967 by Jocelyn Bell Burnell, staring at some chart recorders and seeing that there was a little bit of scruff in those charts, which eventually led to the discovery of the first pulsar. Actually, that first paper contains the first 4 pulsars that were discovered. And these very quickly came to be recognized as rapidly rotating neutron stars with emission along the magnetic field axis, which might be offset from the rotational axis, acting like a lighthouse in the universe. And the idea is that as we observe these pulsars very frequently, we can build up very sophisticated models of when we expect those pulses to arrive. These are essentially metronomes in the sky, and we can predict with high accuracy when these radio pulses should arrive. Anything that causes a deviation to the arrival times of those pulses could be some form of noise, could be due to interstellar medium effects, could also be due to gravitational waves. So here's the idea, vastly exaggerated, the universe is not this kind. Gravitational wave propagated into our galaxy through the Earth pulsar line of sight. And as it does so, it's stretching and squeezing space-time, changing the proper separation between the Earth and the pulsar, and causing the arrival times of these radio pulses to be a little bit earlier, a little bit later than expected. However, the original class of pulsars that were discovered were not sufficient in their timing accuracy to allow us to achieve this kind of detection technique. What we really needed was the discovery of millisecond period pulsars in 1982, which have much better timing precision. They tend to be less glitchier. They tend to be have fewer offsets in their timing properties. And they're ultimately what we use in forming these pulsar timing arrays, millisecond period pulsars, or recycled pulsars. Now, since this is a physics colloquium, I feel like I can show some equations and people won't balk at me. How this works really is that the apparent change in the period of the pulsars, the arrival times of the pulses, is that you've got a change in the metric perturbation between the emission of one pulse to the next. So here's the original pulse, here's the next pulse, and you're looking at metric perturbation changes over that very small time, and then projected against a unit vector pointing towards the pulsar itself. And this is then an integral of the entire photon path from the pulsar to the Earth. Now, since the pulsar period, which is milliseconds, is much, much smaller than the gravitational wave period, you can just do a first order expansion of this metric perturbation term here, and it becomes a fractional change in the apparent rotational period of the pulsar that is just given by the first derivative of the metric perturbation itself. If you tighten this up a little bit and you take a solution for the metric perturbation that is just, say, a plane wave, you end up getting that the apparent redshift induced in the arrival rate of these radio pulses is given by some geometric factors up here. You can think about this term up here as really the detector tensor for pulsar timing. And then we've got this term, these terms here, which are the difference in the metric perturbation of the gravitational wave arriving at the Earth versus arriving at the pulsar. And these are sometimes called the Earth term and the pulsar term. And this is an important nuance I wanted to flesh out a little bit more, because what this gives us is a record of the gravitational wave passing the Earth and passing the pulsar. And the lag time between those may be thousands of years. The idea that we could get an imprint of gravitational waves passing by pulsars thousands of years before the present day is enormously tantalizing, but it does require that we have accurate distances to those pulsars themselves. So here's what the picture is. We've got the Earth, we've got pulsars, we've got, say, a binary source up here, and we've got a gravitational wave propagated through our network of pulsars. We get one component of the redshift to the arrival rate of the pulses, which is caused by the common jiggling of the Earth. Okay, that is the Earth term is going to be up to some geometric modifications common in phase between all of the pulsars. What is different between all of the pulsars is this jiggling of each, and that depends on the line of sight to the pulsar and the distance to the pulsar. Okay, but we get these two imprints, and like I said, they could be lagged by thousands of years. And while we're looking at these binary systems, these are, like I said at the start, potentially 10 to the 8 to 10 to the 10 solar mass binary systems. it's unlikely that they'll be evolving much over the 15 to 20 years that we can stare at them through pulsar timing. However, they stand a reasonable chance of evolving over thousands of years. And so if we can leverage this pulsar term, we can stitch lots of these pulsar terms together, giving us different lines of sight to the pulsars, different lag times, and potentially seeing the chirp of the binary system, due to its gravitational wave-driven evolution over thousands of years. But like I said, that's rather demanding, but we have some strategies to potentially do that in the future. Now, we don't just look at one pulsar. This is giving you an indication that we would like to use several pulsars to do this, more than several, many. Because the gravitational wave signals we're looking for can appear very similar to some noise properties in the pulsars themselves. So instead of just relying on looking at one phenomenally well-timed pulsar, we look at many pulsars and then correlate the information from all of them to give us more accurate detection statistics, something we can rely upon. And so this is a representation of the NANOGrav pulsar timing array as it currently stands. There are 68 millisecond pulsars in here. Earth is somewhere in here. And ignore the lines. The lines actually mean nothing. They're just an artistic rendition that looks kind of cool. But what's important are the relative rotations of the pulsars themselves, which are in proportion to each other, but really are at millisecond rotational periods. So it's a not insignificant chunk of the galaxy that we're timing these pulsars over, with a range of distances from hundreds of parsecs out to a few kiloparsecs. Now, the idea of building a pulsar timing array is that if we have a large number of gravitational wave sources that are emanating from all over the sky, they can all affect the timing properties of pulsars. And so, for example, you've got three pulsars here, red, orange, and blue, and these different pulsars are responding to gravitational waves coming from all over the sky. As they're responding to gravitational waves coming from all over the sky, what you end up getting is not a nice monochromatic signal or a nice chirp, but you seemingly get random noise, random effects. And that's because it is a somewhat random accumulation of sources. Now, it's a stochastic gravitational wave signal. And you might look at this and wonder, how on earth could you possibly go about detecting this kind of signal? Its time series just looks random. And we probe it through the statistical properties of this time series, but we also leverage the fact that this time series is correlated with this time series, which is correlated with this time series. And the correlation only depends on the angular separation between these pulsars on the sky. And this distinctive correlation curve, which lies at the heart of all of our detection statistics for the stochastic gravitational wave background, is called the Helens and Downs curve, which was worked out by Helens and Downs up the road 40 years ago at JPL. This is the signature of a statistically isotropic gravitational wave background in a pulsar timing array experiment. And because it's a statistically isotropic gravitational wave background, the only angular scale that actually makes sense in this kind of curve is like I said, the angular separation of the pulsars on the sky. It's quadripolar in shape. It does not come back up at 180 degrees to the same level that it had before. If you're interested in knowing why it doesn't come back up, ask me at the end. But at the moment, this is our chief detection statistic for the stochastic gravitational wave background, assuming that it's isotropic. Now, I'd like to try to understand or help people understand a little bit more about what this curve actually means. This is my best effort at forming some sort of graphic or visualization to interpret what the Helens and Downs curve actually means. This would be an example of a statistically isotropic gravitational wave background. And imagine we just plonk down a little pulsar there in green. And let's take a look at how this pulsar responds to gravitational waves coming from different parts of the sky. So this is how this pulsar would respond to gravitational waves coming from different parts of the sky. There are regions where it positively responds, negatively responds. That's still fine. It's just a negative in front of the response. And then the purplish regions are where it has very little sensitivity to gravitational wave origin directions. Another pulsar would look different. It would kind of fill in some of those regions of insensitivity. And this might be the kind of response map you would look at if you were interested in resolving individual signals. But if you're interested in finding a stochastic gravitational wave signal, then your process is to correlate signals together. you form 2-point correlation statistics. And so what we should really do is correlate these response patterns as well. So here's what the correlated response pattern looks like between these two pulsars. You get this region of positive correlated response, negative here, and then regions where this pair of pulsars is insensitive to the gravitational wave background. So if you want to convert all of this information, this entire map into one number, you integrate over the sky. You integrate the correlated response pattern over the entire sky. So we take the power of the sky, which for this example is just even, it's an isotropic background. You multiply that by your correlated responses, and then you integrate over the sky. And you will get a single value, which for this pair of pulsars actually turns out to be roughly 0. So there are regions which are balanced in positive responses to negative responses. But let's do this for many, many more pairs of pulsars. Let's do this for a pair of pulsars that is close together. In this area, we've got many regions which are positively correlated. And so when we sum over the sky, we get a positive number. We keep doing this over and over again until eventually you see that we've mapped out the Hellions and Downs curve. So this is no more than how pairs of pulsars in a pulsar timing array experiment respond to an isotropic gravitational wave background signal. Now again, this is a physics audience, so I won't shy away from showing at least one equation here. It's proportional to the overlap reduction function that is dealt with in LIGO and LISA. It is the analog of the overlap reduction function for pulsar timing arrays. Technically, there is a frequency-dependent part of this. However, in the frequency and pulsar distance regime that we're in, it doesn't matter. It's completely immaterial. Okay, so frequency times pulsar distance for us is greater than 10, and that saturates this frequency dependence and means that this frequency dependent factor here is roughly just 2 when you've got the same pulsar and 1 if you've got distinct pulsars. So it's just a doubling effect if you've got the same pulsar. Now, there are lots of different collaborations around the world that are involved in this effort. Here's NANOGrav, which, as Sterl said, is the North American Nanohertz Observatory for Gravitational Waves, using these radio telescopes, Greenbank. Arecibo we don't use anymore, unfortunately, since it's collapsed, but it's still a huge component of our historical data sets and still very important when we do our data analysis. We have some observations from the VLA, also Chime in Canada, and we have huge hopes for DSA 2000 in the future as well, which I'll talk about towards the end of the talk. European Pulsar Timing Array has access to these great facilities. We've also got newer collaborations such as the Meerkat Pulsar Timing Array. Meerkat is a precursor to the Square Kilometre Array in South Africa. The Indian Pulsar Timing Array using something like GMRT, the Giant Meter Wave Radio Telescope. The CPTA using FAST, which is the 500-meter aperture spherical telescope. And then another historical pulsar timing array is PARCS, the PARCS Pulsar Timing Array. And we all work together with the kind of umbrella consortium of the International Pulsar Timing Array. And again, as Sterl intimated, and as I hope people have heard about, we had a bit of a breakthrough last year where we found the first evidence for this statistically isotropic gravitational wave background, evidence in our data sets of cross correlations in the timing properties of pulsars that conform to the Hellions and Downs curve. So here's that black dashed curve, which represents the Hellions and Downs curve. And this is our kind of best reconstruction of the Hellions and Downs curve from 68 millisecond pulsars in the NANOGrav data, which when you pair them all together gives 2,211 pairs. So we don't show all of those, but we do have to bin them together in a way that respects the fact that these pairwise correlation measurements are themselves correlated, because the gravitational wave background signal is actually quite strong at our lowest frequencies, giving us correlated pairwise measurements. And then different degrees of significance in the other pulsar timing arrays. But this is a real watershed moment for us. It is the start of a new stage of this field. And I'd like to take a moment to call out the great people that worked on the NANOGrav results here, some of whom are in the audience: Katarina, Pat, and Joe Lazio is not here. Kurt is, Sophie is here, and Marco as well. So if you're not here, I apologize. If I missed someone, I really apologize, but I think this captures most of the team here that made huge contributions to these results. Now, beyond these initial results, we were joined just about a week or so ago by new results from the Meerkat Pulsar Timing Array, who produced their first results from over 60 millisecond pulsars, finding evidence as well for Hellions and Downs correlations in their data set. It's a much shorter baseline that they're observing pulsars over. It's a more recent experiment. And so there's little that they can say about the spectrum of gravitational waves, the sources of gravitational waves, but they do have this initial evidence for Helens and Downs correlations as well. Now, for the aficionados of detection statistics in the audience, here's our extinction curve looking at statistical significance of Helens and Downs correlations in the data set. Obviously, we don't just quote raw detection statistics. We have to calibrate those with some background distribution. And that is incredibly hard whenever your signal permeates your entire data stream. So how do you do that? We can't just use time slides or other techniques that are used for transient gravitational wave signals. We've got a series of different techniques to emulate that kind of process called phase shifting and sky scrambling. And we also had a team that was able to work out the analytic background distribution as well. So through a variety of different background estimation techniques, we've estimated that the NANOGrav results give about 3.5 to 4 sigma significance. So depending on your linguistic choices, we have evidence for a gravitational wave background signal. But what's more than that, we have the historical growth of those detection statistics over time. We have the ability to forecast into the future what that detection statistic will get to with new data, with new observations. And we also have these independent pulsar timing array results from our partners across the world that we can track as well. We have an effort ongoing to combine our respective data sets together and give an even stronger result. Yeah, and so here are the exact numbers for the different pulsar timing array collaborations. So roughly hovering about 4 as the average detection significance at the moment. Now, what are we looking for? I told you at the start that as we go lower in frequency, we get to more massive compact object binary systems. But our detection process is kind of the process that LIGO has done, but in reverse. Instead of looking at individual sources first, we're seeing every single source first, and then we're hoping to resolve individual ones out of the confusion background after the fact. So the confusion background, we think, is formed from a large population of supermassive binary black holes, all resounding together, forming a source of stochastic gravitational wave signal that we have to pick apart after the fact. So the process by which supermassive binary black holes will come together after the collision of galaxies was first sketched out by Begelman, Blanford, and Rees in 1980. There was the well-known final parsec problem, which now seems to be a problem of exactly which processes are needed to resolve the final stage of dynamical evolution of the black holes before the gravitational waves take over. And then the prediction for the characteristic strain spectrum expected from a population like this was given by Sterl in 2001, where the characteristic strain should be roughly a power law that goes as f to the minus 2/3. But I do want to caution that when we look at the strain spectrum, when we try to measure the strain spectrum, we shouldn't expect to get bang on f to the minus 2/3. This is a discrete population of systems. And so there will be some underlying source of variance in this population as well. We have one realization of a draw from a population. And so while we will be close, we hope, to minus 2/3, we shouldn't be using that as our North Star. So in fact, here's, well, first of all, before I get to that, what we actually look at in pulsar timing experiments are the power spectral density of the timing residuals, the timing offsets. So frequently in our papers and our talks, you'll see a reference to another factor called gamma, which is related to alpha. It's related to this f to the minus 2/3, but frequently you'll compare to 13/3, which is the exponent of the power spectral density of timing offsets. If we look at that for the European pulsar timing array results, you see that it's shallower than 13/3. But also, we have a huge amount of variance here that a population of supermassive binary black holes could give us. It's not just 13/3 or f to the minus 2/3 that we're trying to get close to. That is the ensemble average. It is not what we expect from one realization. Now, if we compare the results across different pulsar timing array collaborations over the last year, what you get is broad spectral consistency. So a power law seems to be a good fit to the spectrum that we've recovered. Up here, we've got gravitational wave frequency. Then we've got the sort of RMS timing offset produced by the gravitational wave background signal. And the different violins here are just different Bayesian representations of the power spectrum. from different collaborations here. So that's the Bayesian spectrum, different samples from the joint posterior in gray. And then on the right, that's that Bayesian spectrum translated to power law fits with an amplitude and then a spectral index, which if you go from f to the minus 2/3 to the power spectrum of the timing offsets, you get this 13/3, at least as a guide. And so we're a little bit shallower, but we're not too far off that. We're well within the kind of Poisson fluctuations expected, Poisson variance from a population of discrete systems. However, I'll say let's be careful with our spectral characterization at the moment, because we've been using very simplistic noise models and at least noise models that are common descriptions across all of the pulsars. And there's an ongoing effort to have bespoke models per pulsar, taking into account different behaviors, different lines of sight that give different kind of interstellar medium effects in the different pulsars. And that will firm up and give us more reliable spectral characterization. So this is our first effort at getting the spectrum of the background, but I shouldn't be surprised if there'll be some sloshing around as we improve our noise modeling in the future. Spectral characterization is influenced by the most well-timed pulsars. So what we showed in the paper a couple of years ago, and then Aaron Johnson showed in 2022 as well, is that even though the gravitational wave background detection is conditioned on many pulsars, many pairs to give that Hellions and Downs curve, it's the most well-timed pulsars that influence the spectral characterization the most. So we do have to do better with our noise modeling. What about the properties of the spectrum we've recovered? Does it at least look sensible when you compare it to a population of supermassive binary black holes and you compare it to other astrophysical models? The answer is yes. A population of supermassive binary black holes can explain the signal. However, we do seem to prefer the kind of largest amplitude models, the models that prefer the highest normalizations of the MM-Bulge relationship and that have relatively short binary lifetimes, fewer than a few gigayears. We get qualitatively similar results across the different pulsar timing arrays. This is just NANOGrav's result for the amplitude of the gravitational wave background for a power law, compared against some of the results in the literature here, and we're well within the spread and encapsulating these models. Now, there has been a question over the last year, and people trying to confront it, is the amplitude too big? Is everything that we're seeing actually a gravitational wave signal, or could we be conflating with noise? And I think the answer could be that we're conflating with some noise, and that could be pushing up the level of the background a little bit, but not entirely. So earliest work here about a year ago was Sadopoulos, Zaldariaga, and Collier, who used the Solkin argument to say that if you take the population of supermassive binary black holes as given by AGN in the universe, and you try to work out what the typical mass of binary systems contributing to the PTA results is, you get the typical mass is roughly 3 × 10⁻⁻. That is gigantic, and it seems to imply an unseen population of nearby extremely massive black holes. Now, these are their models down here, characteristic strain amplitude here, these are their models, and then these are some different PTA models. Now, I would argue that this is a big error bar, and this actually encapsulates these. There's not too much of a statistical tension here. But even more so, we had a result come out about 6 months ago from Leopold and Ma, Changpei Ma at Berkeley, who constructed a new galaxy stellar mass function that matched on to the massive survey of nearby massive galaxies, which was tuned to match this massive survey at stellar masses of greater than 5 × 10⁻10 solar. 5 × 10⁻11 solar, sorry. And once they do that, their newly constructed galaxy stellar mass function seems to show no tension with the results produced by NANOGrav and other pulsar timing arrays. So I think there's not significant tension with existing models of supermassive binary black hole populations and other models of massive black hole behavior. But there remain interesting questions of what exactly these results mean for massive black hole dynamics and astrophysics. Something that I and my group have been working on recently is trying to understand the gravitational wave background ensemble distribution. That is, how do we incorporate all sources of possible variance into our interpretation of the gravitational wave background? So like I said, there's one source of variance, which is you've got a discrete population. That discrete population is one draw from a distribution. How do you fold in that possible population or realization spread into your interpretation of the background. There's been some historical work on this, and then lots of work recently to take into account the population spread. Something that William Lamb, a student of mine, and I worked out about 6 months ago are the moments expected from the omega GW, the fractional energy density of the gravitational wave background, over the entire ensemble of possible realizations. And what we found is that the standard deviation of this gravitational wave background energy distribution divided by the mean just scales as f to the 11.6, and that's independent of what is driving the systems, what is the dominant driver. It doesn't matter if gravitational waves are the dominant driver at a particular stage. What is true is that just from the Poisson variance, the standard deviation divided by the mean goes as f to the 11.6. And then you get higher moments as well. The skewness squared of the kurtosis is constant. And that's, to me, that seems like a very clean probe of discreteness effects in the gravitational wave background distribution. So if you see upticks or deviations or outliers in your strain spectrum, then you can see if those deviations actually conform to the statistical properties in the moments that we've worked out here. Another thing that we'd like to do is to actually build models that can translate from the data into posterior distributions of the environmental parameters, the massive black hole dynamical parameters, the demographic parameters of massive black hole systems in the universe. And how do you do that? So one answer that we've been developing is to train a normalized and flow emulator. We can't run our supermassive black hole binary population simulations live as we do our analysis. So we build an emulator, like many other fields in physics nowadays. We train that normalized and flow emulator on a library of supermassive black hole binary population simulations that have been run at different environmental conditions. And what we end up with is a very fast way of predicting what the shape of the spectrum is, given some input environmental, dynamical, demographic conditions for the population. So this is something that's being developed by a postdoc at Vanderbilt, Nima Lal, and then the holodeck team, as we call it, within NANOGrav. Holodeck is our supermassive black hole binary population simulation software. Holodeck, hopefully some people recognize the reference to simulations. All right, previously we'd used Gaussian processes to do this emulation. That had some limitations. It was assuming that the ensemble distribution was Gaussian. And same for another dense neural network approach that was built this year. It assumed in the ensemble distribution was Gaussian, which it's not. Another more fundamental source of variance is just that we have wave interference at these low frequencies in the small number of cycles that we have within our data sets. And so that has been studied most recently through the shape of the correlation curve. So even though the Hellions and Downs curve, this black line, is the ensemble mean, wave interference effects mean that you'll have realizations where it looks, you've got fluctuations from the Hellions and Downs curve, just from this fundamental source of wave interference or cosmic variance. What we're now looking at is how wave interference influences the shape of our spectrum. So again, this deviates you away from the simplistic assumption of f to the minus 2/3, and now, excuse me, I've gone into omega GW, so really it should be f to the 2/3. And you've got fluctuations around that, again, just due to wave interference. And we started the literature to try to see if there was someone had worked out what the probability distribution of the energy density of a gravitational wave background should be. And we couldn't find anything. We found some moment matching attempts, so people working at the moments of this probability distribution, but we didn't find what the actual solution is for the probability distribution of the background. If we just simulate this and look at what the distributions are, it's Gaussian-ish, but there's a long tail. And so we tried to do moment matching as well. And we also tried to think through what might be creating this if we built up the background from a large number of independent identity distributed exponential distributions, which it should be for one source. And what we found out is that the probability distribution for fractional energy density matches an airline distribution, which is just a gamma distribution with an integer shape parameter. It matches it really well through moments and through fits. So our leading hypothesis is that the reason why the shape parameter for this airline distribution is 5, it's always 5, is that it's a number of degrees of freedom for a spin-2 massless particle propagating in 3 dimensions. This is ongoing work. I figured if there was any place I could come to where people could dissuade me of this notion, it would be here. So I'm open for discussion afterwards, but we think we've worked out what the probability distribution for the energy density of gravitational waves actually is. Now, we're looking at a stochastic gravitational wave background signal. There are more properties we can prove than just the spectrum. And there are more questions that we can answer. So first of all, is there a gravitational wave background signal? Well, I would argue yes. But what is its spectrum? Is it anisotropic? Is it polarized? Is it even stationary? I think these are still open questions and characteristics of the background we have yet to be able to answer. So first of all, then, if we characterize the gravitational wave background, we're looking at the fundamental statistics of the background, which is describing that the Fourier modes themselves are Gaussian distributed. And built into this is the assumption of Gaussianity for the Fourier modes. Then we assume that the background is stationary through this term. We assume that it's uncorrelated across the sky. There should be nothing connecting one gravitational wave source across the sky to another. And we also assume that it has some polarization properties. Now, if it's really a population of supermassive binary black holes, those individually are elliptically polarized, but there should be nothing that really causes there to be an overall polarization. An overall polarization, statistically speaking, nothing should be lining up the binaries in a certain way to give us polarization on average. We can break down the polarization properties of the background just like you break down the polarization properties of the CMB. You can look at the intensity and then the different Stokes parameters within that polarization tensor. So the intensity is just the squared sum of the plus and cross polarization amplitudes. And then the different linear polarizations are different subtractions or overlaps of the polarization amplitudes. And then circular polarization is another property we can probe too. We start off with intensity. The frequency dependent part of the intensity is what we probe through measurements of the spectrum. Okay, so that gives us a measurement of the spectral shape. There is an omega dependence here, omega being directions in the sky. So we can try to prove the anisotropy of the background and see if there's some directional dependence to the intensity of gravitational waves. So ultimately, we'd like to go from a very coarse map like this and resolve to higher and higher multipoles until we get to the point where we can start to actually see individual hotspots and potentially use those to herald individual sources that we can pull out of the confusion background signal. Unfortunately, we have no evidence of anisotropy yet. What we do see is that we have best upper limits on this anisotropy closest to pulsars. So it's proximity to pulsars that really dictates how sensitive we are to anisotropies and even to individual sources. The closer you are, the closer our source is to pulsars in the sky, the more sensitive you are to that particular direction. These techniques are adapted, from CMB techniques and from LIGO techniques, absolutely. Hopefully we fed back some techniques as well into gravitational wave anisotropy efforts. We think that based on supermassive black hole binary population modeling, we could see anisotropy from such populations within about 5 years. And we do know from the previous variance calculations that we did analytically and then our numerical experiments that anisotropy should increase with gravitational wave frequency. Because as you go higher in frequency, the occupation of the frequency bins diminishes, and you end up with more fluctuations. The stochasticity of the signal starts to break down. So we have that to leverage, and we also have our techniques to leverage to try to determine whether we've got gravitational wave anisotropy. Now, an important aspect of this anisotropy is that it's not going to be probing something fundamental about the nature of the universe. It's not like the CMB. Rather, it's a map of supermassive black hole binary population in the relatively nearby universe. So it's more likely that the anisotropy will derive from so-called shot noise, individual systems, than giving some indication of the positional distribution of galaxies and supermassive black hole binary sources. So think of it as a map of the bright single sources rather than giving us information about large-scale structure. Now let's go on to polarization. The linear and circular polarization are these combinations of plus and cross again. We have no evidence yet of circular polarization because that would require us to have evidence of anisotropy. In pulsar timing arrays, we only get access to the circular polarization aspects through the higher multipoles of the intensity distribution, higher multipoles of the maps that we can access. So we need anisotropy to get evidence of polarization in PTAs. However, the overlap reduction functions can now all be analytically computed. They've all been worked out within the last few years or so. And so these are searches we can actually do right now. If we do have circular polarization at a statistically significant level, I think that would be very interesting. That either points out that you've got a threshold individual source that we're not able to accurately extract or well extract from the background. And so it's giving you some anomalous polarization, or there are some cosmological processes that can introduce polarization, broad scale polarization of the background as well. So this could be one way that we can try to disentangle the origin of the background as being either from a population of compact binaries or a fundamental cosmological process from the early universe. This is why I'm at least interested in polarization as an avenue to try to discriminate the origin scenarios. And potentially with something like the SKA, we could probe polarization to the level of a few percent once SKA really wraps up in the end and start of this decade, the start of the next decade. Is the gravitational wave background stationary? There were some results in the Parkes pulsar timing arrays papers that they indicated could be due to non-stationarity of the background. That is, the statistical properties changing over time. And to do so, they took different slices of their data set. They looked at the statistical properties and they saw some changes, some slight tension in the results over time. But I would argue here that they have 15 to 20 years of data. Their slices of data are quite large as well, and therefore they're not independent. They've taken dependent slices of their data and they're looking at the statistical properties changing over time. And there's really not that much evolution. So I would argue there's no evidence for non-stationarity yet. And in fact, if you take time-dependent models of the power spectrum of the background and you apply that to European pulsar timing array data, then you get no evidence for stationarity in that data set either. It's much more likely that what we're looking at the moment is just variation in these inferred properties due to the time-evolving characterization of noise processes in the data set. We get better at characterizing the pulsars as time goes on, and that's what we're observing. Now, kind of droned on about the background for quite a long time, but let's get to the single sources. We would like to be able to, over time, bring individual sources into focus and not just have this be a stochastic background signal. Interesting behaviors you get in pulsar timing signals due to the pulsar term, this imprint of the binaries evolution from thousands of years in the past when the gravitational wave passed the pulsar. So instead of a monochromatic wave or a chirping signal that you might expect, what you get is a beat pattern, because the overlap of the higher frequency Earth term signal and the much lower frequency pulsar term signal gives you this beat pattern. So the Earth term signal would be this dashed cyan pattern here. That's a higher frequency. And then the lower frequency envelope is given by the pulsar term, the imprint from potentially thousands of years in the past. Things get even funkier if you look at eccentric systems, because something that's even mildly eccentric in the Earth term could be very, very eccentric thousands of years ago in the pulsar term. These are all things that we have to model, and our ability to model them and extract them depend on our ability to measure good distances, precise distances to the pulsars. Unfortunately, we don't have very precise distances in the pulsars at the moment. We need to know the distances to approximately better than a gravitational wavelength. And for us, that's at the parsec scale. We have maybe a few pulsars that qualify in that scenario. Now, in our 15-year NANOGrav results last year, we did a map of gravitational wave signals across the sky and put limits on possible single sources at different points in the sky. Red stars here are pulsars. We've got white diamonds, which are prominent candidates. We've got lots of black points here, which are periodically variable quasar candidates from time domain surveys. And then in the actual colored region here, the map is showing the distance out to which we can effectively exclude the presence of a binary. And at 10 to the 9 solar masses in chirp mass, that's a few hundred megaparsecs. But if you go to a 10 to the 10 solar mass binary as your putative system, that gets into the several gigaparsec scale. Now, there were interesting little hints, and I will say there are little hints in our data sets, little as in only base factors less than 10, but we'll track those over time. There seem to be little fluctuations in the NANOGrav data set of a few, and then European pulsar timing array data sets of a few as well. Like I said, these are nothing to get too excited about, but let's just put a pin in them and look at them into the future. What we can do at least is track them into the future and make predictions about what they should look like in future data sets, which is one of the benefits of essentially having eternal gravitational wave signals. They're not going anywhere as long as we're looking at the pulsars. Some of the opportunities for single sources are multi-messenger, PTA, and time domain detections. So there are two possible paths to making a multi-messenger PTA detection of a single source. That's either we do an all-sky gravitational wave search, we get some broad sky localization of a source, just as exactly as LVK does it, and then we do host galaxy identification and follow-up, okay? So we can localize the supermassive black hole binary signal to its host galaxy. Another possibility is we look at the many binary candidates or plausible hosts that we have at the moment from time domain surveys. We follow those up, we do targeted searches, and perhaps we say that we're insensitive to many of them, or perhaps we can rule out many of them as well. This is an exercise that's ongoing as I speak. Something that one of my graduate students has been doing is following through the entire detection process from an individual source. Try to do essentially a dress rehearsal of what the first single source detected in PTAs will look like. So initially, we're searching for all of the noise in the pulsars, we're searching for the gravitational wave background, and we're searching for single sources. This is not something where we can do a piecewise analysis. We have to do everything at the same time. Now, if you're familiar with the LISA detection process, what LISA will do, this is sort of a mini global fit. This is searching for all of the noise and all of the signals at the same time. And so this localization of a particular source that was injected in our simulated data sets is representative of the kind of early localization we may get of a single source. Inside here are lots and lots of candidate galaxies from a value-added galaxy catalog built on top of 2MASS, the 2MASS redshift survey. And what Polina, my student, has done here is several cuts. You basically look at the mass, the chirp mass, that has been determined from your gravitational wave analysis, and you see if there's tension with the galaxy mass that's determined from other means. So you can rule out certain galaxies as not being plausible hosts of a massive binary black hole, such as we found in this injection. You can do a distance cut as well until eventually you've whittled your number of plausible hosts down to an ideally more manageable number. And this is all just based on coarse properties of the galaxy, the mass, the distance. This is not based on additional information that we get from the inner regions of the galaxy, say by looking at the stellar kinematics, if we did more targeted follow-up. So ideally, this gets us down to a more manageable number of plausible hosts on which we can do dedicated follow-up, dedicated observations to see if there's signatures of binarity in the galaxies. Now, what we observed is that regions that had high density of pulsars had the best sky localization, even if the signal-to-noise ratio was locked to be the same. So if you inject an identical signal-to-noise binary system in different parts of the sky, your ability to localize the source is improved closer to the pulsars in the sky. And that's purely a geometrical effect. You get some effects from the pulsar term, but it's by and large a geometrical effect. So even though you might be on what we would call the insensitive part of the sky, if you're relatively close to a pulsar, you benefit from that proximity. And so you get good sky localization. If you're far from pulsars in the sky, unfortunately, you get very broad localization. Some other work that I've been doing recently with Luke Kelly and an undergraduate at Vanderbilt is looking at the typical properties of hosts that could actually harbor a supermassive binary black hole that would be detectable by PTAs. So it's not just looking at typical hosts of supermassive binary black holes, it's looking at typical hosts of galaxies that could actually be host to ones that are detectable in pulsar timing arrays. And we can extract some typical demographics from that and use that as additional information as well. So in blue here are the underlying distribution of properties from all galaxies. And then in black are the detection weighted properties once we introduce the idea of localizing and finding a single source in PTAs. So they tend to be obviously the most massive and relatively nearby, closer than redshift 0.5. We skew towards more equal mass, just like as you would expect from gravitational wave observations. And then the stellar metallicity, interestingly, seems to pull towards about 2 times solar metallicity for detection-weighted host galaxies. So we can attempt to use this kind of information, again, to cut down the number of plausible hosts on which we would do follow-up. Now, I said at the start, or sort of a few minutes ago at least, that I wanted to do multi-messenger PTA detection, not just gravitational wave detection with pulsar timing arrays, but to fuse that with information from time domain candidates, periodically variable quasar candidates. The idea being that gravitational wave and EM information map the orbital dynamics of these binaries in different ways. And if you could do a coherent joint multi-messenger analysis of these systems, then you could improve your parameter estimation, maybe even improve your detectability of these kinds of systems. So gravitational waves for a circular binary system have 2 times the orbital frequency of the system. But then if you've got some other mechanisms that Elias is much more experienced and knowledgeable about, if you have some other mechanisms that can produce EM variability of a binary system, say involving disks around the black holes, maybe even a circumbinary disk around the entire binary system, then one of those mechanisms is called Doppler boosting. That's really just Doppler boosting of radiation coming from the mini disks around each of those black holes. And that might be expected to track the orbital period of the binary itself. And if you're inclined very, very favorably, a black hole can actually lens radiation from the mini disk of another black hole behind it. And so you might get these interesting self-lensing flares that accompany the Doppler boosting behavior. Okay, so you might, have different mechanisms that can give you sinusoidal periodicity, but something like a self-lensing flare to me is pretty characteristic of a binary system, especially if it's a primary lensing flare and then a secondary lensing flare. So the dream I have is to fuse all of this information together and try to actually do a simultaneous multi-messenger analysis of these kinds of candidates. And some work done by Maria Carisi, who was a postdoc at Vanderbilt and a postdoc before that at Caltech, now faculty at Washington State and also in Crete. She did some work a few years ago which showed that there is a favorable overlap in the parameter space of binaries that could be detectable in gravitational waves and also in Doppler boosting, in this Doppler boosting mechanism. So these are different sensitivity curves and sensitivity regions for an early NANOGrav data set, a very near future IPTA data set, the SKA in 2034. And if you compare that to Doppler boosting, you would get from binaries that are inclined by different amounts, there is a reasonable overlap for the most massive systems and then for long period binaries that PTAs are most sensitive to. So I've talked about the gravitational wave background, I've talked about single sources. What might we be looking at for the road ahead? We now have this initial evidence for Hellings's and Downs correlations indicative of an isotropic background in pulsar timing array experiments. As we improve our noise modeling, as we improve our ability to resolve the characteristics of the gravitational wave background, we will also improve the spectrum measurements. And that will tell us more about what is driving the supermassive binary black holes that are the likely origin of this signal. It will tell us more about the overall demographics of those systems. And if there is some tension, perhaps it's also indicating some other unknown source. There's a huge group of people that's interested in trying to interpret our signals as some cosmological processes from the early universe, whether phase transitions or primordial gravitational wave backgrounds. That is a possibility in this band as well. Beyond that, we will start to extract individual binaries from the confusion gravitational wave background. We will do it one after the other. And it's unfortunately something that is cumulative, so we can't just extract and move on. We will just have to model and keep track of that and keep building up the number of sources that we can resolve out of the background. After that, like I said, my dream is that we have a multi-messenger supermassive binary black hole system. This is also a prospect in LISA, but it's a prospect that could happen right now, or at least within the next few years from pulsar timing arrays. Once you have individual sources detected and some statistical understanding of the gravitational wave background and the broader population, that gives you more detailed information about the origin population of gravitational waves here. And at some point along this road, LISA will launch, currently slated for August 2035, which will tell us much more about lower mass black holes. And I say lower, but I really mean sort of 10 to the 4 to 10 to the 7 solar mass black holes. So not the same systems that we're seeing in pulsar timing arrays, but part of the broader landscape of massive black holes that live in galaxy centers. And that really fills in a lot of the picture for massive black holes in the universe. So the next step for the International Pulsar Timing Array is to fuse our data sets together. We're currently producing a 120 pulsar data set, which is the combination of all of the pulsar timing data sets that came out last year. It is a process, okay? We have to connect all of these data sets together and make everything coherent and combined. That is something that takes a while, but once it is done, ideally we should get more significance, perhaps even the 5 sigma evidence that the community wants. After that, we'll be tracking some of these periodic quasar candidates with something like the Vera-Rubin Observatory. So we can attach historical candidates, more recent candidates as well, from CRTS, pan-stars, ZTF, and then match that onto the baseline of LSST, and then start doing more targeted searches for supermassive binary black holes with PTAs as well. Really a big component, a huge component of NANOGrav's future is linked into DSA 2000, which is led out of Caltech here by Greg Hellerman. I'm sure you've heard many talks about it. It's the Deep Synoptic Array 2000. It'll be a series of 2,000 5-meter radio dishes sensitive to radio frequencies between 0.7 and 2 gigahertz. And in this array, NANOGrav would have 25% observing time. So this is more than just making up for the loss of Arecibo. This has given us access to huge surveys and more robust timing of pulsars into the future to extend our array and stay competitive into the future. And of course, one of the big game changers for radio astronomy in the future as well is going to be the advent of the SK era. Now, just to add on to what DSA 2000 will be able to do, it's a big data problem. It's going to require very nimble and very quick analyses. And something that the Caltech team here on NANOGrav is working on are much, much faster gravitational wave searches, GPU accelerated gravitational wave searches, even deep learning accelerated gravitational wave searches using techniques like variational Bayesian inference and normalizing flows. So it's moving us into this era where we're not, just doing serialized analyses anymore, but we're trying to speed up, really juice up our gravitational wave searches because these data sets just keep getting longer and longer and longer. It's a cumulative effect. We need all of the data to be sensitive, but we also need faster algorithms to search over the possible phase space of different models. I'll finish off with what I think are some open questions in PTA science at the moment and things that you might be interested in getting involved in. Who ordered the background? Where does it come from? What is its origin? Is it anisotropic? Is it polarized? This will give us some clues to the origin. How much information can we mine from the spectrum of the gravitational wave background before we hit some fundamental cosmic variance limit, beyond which we're just probing random fluctuations? Could we potentially cross-validate the PTA evidence for gravitational waves with something like astrometry, large astrometry experiments like Roman, which could access similar frequencies of PTAs just by looking at angular deflections caused by gravitational waves instead of timing deflections? Beyond that, beyond the studies of the background, when will individual gravitational wave signals be found from PTAs, and what will that process look like? What will the emergence of a single source look like? And will that be associated with compelling multi-messenger detections? And then finally, what is the new physics and fundamental physics that PTAs can probe that's distinct from other physics experiments? We do have access to different models within the PTA detection band, primordial gravitational waves, phase transitions, other topological defect signatures. Could that be something that we could measure or constrain well in the PTA band? And I haven't even talked about beyond GR tests. We lack waveform sensitivity, it's true. We're much less sensitive than ground-based experiments for waveform tests of beyond GR theories. But we do have great polarization constraints just by virtue of the many different lines of sight to different pulsars. So there's lots we can do here. It's only 1.5 years since we found this initial evidence. The work is ongoing, and hopefully I've piqued your interest in the questions to come. So thanks very much.
Questions? There it is.
Yeah, thanks a lot for a nice talk. One question on I think on a study that the collaboration recently did, which you did not mention, that was about whether you can probe the environment of the supermassive black holes and see something that's gaseous driven and spiral versus dark matter versus free body. Can you say some more about that?
Yeah, so at lower frequencies in the PTA band, you're obviously probing more widely separated supermassive binary black holes, and in that regime, we might expect some contact with the environment. That would produce deviations, turnovers in the spectrum, but what we're seeing at the moment is that there might be a turnover that we can fit, but it is not favored in our model selection. The base factor is, I think, less than 2 versus a power law, which is the simplistic description.
In fact, this interference, as you mentioned, I wondered, can you put any lower bound on the finite number of sources in your background, just from the effective number of samples you have as a function of angular scale?
Yeah,
and the interference of the beam?
I think possibly. I don't know if we've done that exercise yet, but I do think it's possible by looking at the statistics of fluctuations that we could actually say which N regime we're in. Are we in the large N regime, or are we in the regime we've got a small N? Not off the top of my head that I can think of, but there has been a huge amount of work on this area recently. Maybe if someone else in the audience knows, they can answer.
Ask an elementary question. You mentioned this correlation function. Is it the correlation in the Earth term?
Yeah, there's a correlation in the Earth term. We make the assumption when we do our cross correlation analyses that the pulsar terms are they're oscillating rapidly on the sky and they decorrelate very quickly. Yep.
That's good. When you count modes like polarization modes, angular modes, and also frequency modes, how many modes do you have that above the noise?
So how many modes are above the noise? In the frequency spectrum, we have about 10 modes that are above the noise at the moment. In the anisotropy spectrum, we have no modes that are above the noise. We have no evidence for anisotropy at the moment, but our angular resolution would be something like L max of 5 or 6, just based on the number of pulsars we have and the kind of angular resolution you'd expect from that. Katarina, what can I tell you you don't know?
So what do you think you can learn depending on whether about their physical model, depending on whether you see an individual binary or an anisotropy first?
That's a good question. So let me unpack the question a bit more. I think there could be 2 possible paths to find in a single source in PTAs. Possibly that it shows up first as like a excess bright spot in our anisotropy searches, or that just a template-based search wins out immediately, and you don't see anisotropy first. We're actually doing this sort of exercise at the moment in my group, and what we find is that even though I assumed you would see a bright spot in anisotropy first, really the template-based searches win out. So you get higher base factors for a Gaussian stochastic background plus a waveform model single source than for an anisotropic gravitational wave background. I did not expect that. I assumed it was going to be the opposite. It's possible we haven't looked at the full expanse of different scenarios, but it seems like even though we've got a huge number of parameters in single source search, they're mostly just filling their priors. And so you don't get a penalty from that. And it seems like that wins out overall to have a single source model rather than just excess power in a part of the sky.
I had a question. So the traditional lore was that the gravitational wave background expected spectrum was quite steep relative to the pulsar red noise. And so you always do better by going to longer time scales. But Meerkat and the FAST seem to have short baselines and detected things very quickly, or so they claim. So I guess Do they have better pulsars or better, more homogeneous timing, or how do they succeed there?
They curated a pulsar data set in a way that was quite different from what the historical PTA collaborations did. They started with a huge number of pulsars first, and then just looked at them contemporaneously. And since your detection statistics are based around this Helens and Downs curve, it's number of pulsars, it's number of pairs that matters for getting the signal to noise. For evidence of the background, you want many pulsars, even if they're not particularly well-timed pulsars. You know, a lot of mediocre pulsars is better than a few really, really extraordinarily well-timed pulsars. And the other side of that is if you want to actually say something about the gravitational wave background, you want to say something about the population and the underlying, you know, conditions, you need the long time scale, you need the long baseline, and that's what they don't have at the moment. But they will.
So you're saying that even sort of crappy ones for a short time are sufficient, even though they don't tell you anything about the spectrum,
Yeah.
basically. So I guess going forward, is it clear, is there different approaches to timing or curation of pulsars which are likely to improve things?
Simply connecting our data sets together is going to be a major leap forward. So in the IPTA data release 3, it's going to contain all of the NANOGrav data from last year's results, all of the European, Indian, Parkes pulsar time array data, plus Meerkat, and potentially other data sets as well that we can connect in. So that will be 120 pulsars at least, maybe some beyond that. And then with something like DSA 2000 being an option in the future, that's going to massively expand our array as well.
Because are people being more careful about changing wiring harnesses and computer delays, which I guess in the past always required additional parameters or.
This is something I don't know anything about, unfortunately. I'm not a really strong.